بسم الله الرحمن الرحيم والصلاة والسلام على رسول الله الأمين. السلام عليكم ورحمة الله تعالى وبركاته. In this video session, inshallah, I will explain double sideband suppress carrier or DSB-SC. In the previous lectures videos, we have explained the double sideband with full carrier or the standard amplitude modulation, standard AM, or DSB-FC. And we have found that the AM modulation suffers from two major practical limitations. One, AM is a wasteful of transmitted power because the carrier signal C of T is transmitted along with the two sidebands, the upper sideband and the lower sideband, or the information bearing signal. And the efficiency of the amplitude modulation have been found to be approximately equal to 33%, which means that 2/3 of the power is wasted in the carrier signal. As we know that the carrier signal has no information. The information only resides in the upper sideband and the lower sideband. Also, AM is a wasteful of channel bandwidth. It is a wasteful of channel bandwidth as it requires a transmission bandwidth equal to twice the message bandwidth. So the bandwidth is equal to, we found that it is equal to 2FM, where FM is the highest frequency component in the message signal. So in DSB-SC or double sideband suppressed carrier, the transmitted power is saved here through the suppression of the carrier wave or carrier signal, but it is still suffers from the channel bandwidth as the channel bandwidth requirements for the DSB-SC is the same as for the AM modulation. Basically, double sideband suppressed carrier consists of the product of the message signal with the carrier signal, which give us the modulated signal S of T. Accordingly, the device that is used to generate double sideband suppressed carrier is referred to as a product modulator. So S of T is equal to the message signal into C of T, where C of T is the carrier signal and M of T is the message signal. And if we replace the carrier signal with its expression, so the modulated signal S of T is equal to M of T cosine 2 pi FC T plus phi, where the phi is the phase shift. So assuming that AC is equal to 1 and phi is equal to 0 for simplicity, then the modulated signal S of T is equal to M of T cosine 2 pi FC T. We also know that unlike AM modulation, double sideband suppressed carrier modulation is reduced to zero, whenever the message signal is switched off. If we switch off the message signal, then S of T will become equal to 0. Most noticeably, however, is the fact that the modulated signal S of T undergoes phase reversal whenever the message signal crosses the 0, as we will see later, inshallah. Before we go deeply in the process of modulation and demodulation of the double sideband suppressed carrier, let us first see the spectrum of the modulated signal of DSP-SC. And before that, let us review some important information for Fourier transform. We know that e raised to j 2 pi fct, the Fourier transform, this is the time domain for the exponential, complex exponential signal. The Fourier transform for e raised to j 2 pi fct is delta of f minus fc. And if it is minus here, it will become here just only plus. So the exponential is a pulse. It's just only a pulse centered at frequency fc for the positive and negative frequency. Also, we know that from the Fourier transform table, or the property of the Fourier transform, if any signal multiplied by any of these exponentials, our complex exponential signal, then the multiplication in the time domain will become as convolution in frequency domain. So m of t, we know that as we shown in the previous amplitude modulation, m of t in the Fourier, when we take the Fourier transform for m of t, it will become capital M of f. This is just the representations of the signal. So m of t is capital M of f, and e raised to minus j 2 pi fc t will become as delta of f plus here, actually plus fc. And for the plus, there is minus. So forgive me for that. So the multiplications of the m of t, e raised to minus j 2 pi fct, the Fourier transform for this is f convolved with delta f plus fc. Okay, so here this is right. Okay, so m of t e raised to j 2 pi fct, the Fourier transform for this is m capital M f minus fc. This is one of the properties of the Fourier transform. Please refer to the Fourier transform table, or revise the Fourier transform as well, because it is easy to analyze the signal in frequency domain rather than in the time domain. So the frequency shifting property, we have m of t, as we said, the Fourier transform for m of t is capital M of f. So here we have the modulated signal, the double sideband suppressed carrier signal, which is the multiplication of the message signal into the carrier signal, which result if we take the Fourier transform for this modulated signal for DSP-SC, then S of f is equal to half capital M of f minus fc plus M of f plus fc. That's why we have revised in the previous slide the exponentials properties, and it is their transformation. So as we said here, cosine 2 pi fct we can be represented by the Euler identity, which is half e raised to j 2 pi fct plus e raised to minus j 2 pi fct. So knowing that, we can take the Fourier transform for m of t cosine 2 pi fct using Euler identity. And by using this formula, we can find easily the Fourier transform for the product of the m of t and the carrier signal. Also, we notice that the pure carrier signal or pure carrier component is not exists in this expression. So we don't have a carrier component. That is, the carrier has been removed or reduced, or in other terms, it is suppressed. So if we plot this Fourier transform using an arbitrary shape, we can use this shape or triangle shape or whatever shapes. So This is here at the left hand side uh, the plot of the M of f, capital M of f, which has a bandwidth of Fm, and we have negative as well here, negative Fm, but the bandwidth is considered only for the positive values. So this is just only an image of the positive bandwidth. So having said that, this is the Fourier transform of the message signal M of t is M, capital M of f, which has frequency of Fm. So this, if we plot this, we will have two components. The message signal has been spaced or has been centered around Fc. So this is the half M of f minus Fc, and this is half M of f plus Fc. So here we have the Fc plus Fm, the maximum frequency, and here we have the minimum frequency, which is Fc minus Fm for the positive part. Also for the negative part, we have minus Fc minus Fm. This is the maximum frequency component, and minus Fc plus Fm, this is the minimum frequency component. So this way, using Fourier transform analysis, it is easy to analyze and visualize the signal in the frequency domain and see the frequency component that exists in our signal. Because in the time domain, we cannot figure out the frequency component. That's why it is very necessary to have some background of this transformation. Actually, you have to master the Fourier transform. So this representation is the spectrum of the modulated double sideband suppressed carrier signal, S of t. So we have this, the shaded area is the upper sideband, and here this is the lower sideband for this component. As well as we have here, this is the upper sideband and this is the lower sideband. And there is no carrier signal, pure carrier signal, as we have seen in the AM modulation, where the carrier signal exists here in the frequency Fc as a pulse with high amplitude compared to the sidebands. So it is very necessary that also, as in the AM modulation, in double sideband suppressed carrier, the carrier frequency should be much greater than the message frequency Fm. So we should maintain that Fc should be greater than, much greater than Fm, where Fc is the carrier frequency and Fm is the maximum frequency component of the message signal here. Now, if the Fc is less than Fm, then there will be an overlap between the sidebands as shown here in this figure. So it is very necessary that Fc should be much greater than Fm. If it is less, then there will be a distortion and we cannot retrieve the message signal correctly as a result. So as I have said, in this way, using Fourier transform analysis, it is easy to analyze the signal in the frequency domain, and that is why it is, as I said, necessary to have some solid background of this transformation. Now let us see the signal in the time domain. Let us now leave the frequency domain and go to the time domain. Let us see the signal. Okay, let us assume this is our message signal in the time domain. This is the message signal m of t, and this is how the modulated signal will look like, where when the message signal crosses the zero, then in this crosses zeros there will be a phase reversal. So we cannot use the simple envelope detector to detect and retrieve the message signal which is in the envelope. Because of this phase reversal, then the envelope detector cannot retrieve or extract the message signal from the modulated wave. Now let us explain the modulation process in the double sideband suppressed carrier as shown in this figure, and as we have mentioned earlier, that the modulated signal can be generated using a product modulators to generate the double sideband suppressed carrier signal or the modulated signal. So here we have the product modulators, and we have the message signal m of t multiplied by the carrier signal cosine 2 pi fct, and the output would be the m of t cosine 2 pi fct. Very simple. This is now the modulated signal. So the device used to generate, as I said, the double sideband suppressed carrier modulated wave is referred to as product modulator. Now, to generate the double sideband suppressed carrier modulated signal, we use two types of modulators: balanced modulator, and the second one is the ring modulator. But in this video session, I will explain only the balanced modulator, and the ring modulator will be left for you to explore by yourself. So, what is the balanced modulator? Balanced modulator actually, as shown here in this figure, consists of two identical AM modulators. So we have here at the top channel the AM modulator, and here we have also at the bottom channel the AM modulators. So we have two identical modulators. These two modulators are arranged in a balanced configuration in order to suppress the carrier signal. Hence, it is called the balanced modulator. So this circuit consists of as we said, the two identical modulators, and we have also local oscillator that generate the carrier signal C of t, which is equal to AC cosine 2 pi fct. This is the local oscillator, and we have the modulating signal or the message signal m of t, which is delivered or fed to the upper AM modulators m of t, and a phase shifted version of the message signal by 180 degrees is fed to the bottom AM modulators. So we have here m of t fed to the AM modulator at the top, and minus m of t is fed to the AM modulators at the bottom channel. So, and we have local oscillators that is given to the AM modulators, to the two AM identical modulators. And we have here, we subtract the S of t, then here we produce S1 of t, and here S2 of t. Then we subtract S2 of t from S1 of t, as indicated here by the minus and here by the plus. Then here the double sideband suppressed carrier or DSPSC will be generated as we said. Let us see the mathematical representation of this circuit diagram. So, as we know that the standard AM signal is given by S of t is equal to AC 1 plus case of A, m of t cosine 2 pi f ct. And we know that AC is the amplitude of the carrier signal, m of t is the message signal, and case of A is the amplitude sensitivity of the modulator. So this S1 of t is the signal from the upper channel, S1 of t, because this is, as we said, an AM modulators, the standard AM modulators that we have studied earlier. So we have here AM modulators, and here we have AM modulators as well. So the standard equation for the AM wave is given by AC 1 plus, as we know, 1 plus S of A m of t cosine 2 pi fct. So this is the standard formula for the AM wave. So we have S1 of t is equal to AC 1 plus Ka m of t cosine 2 pi fct. And for the others, S2 of t is equal to AC 1 minus, because we have here minus m. That's why here we have this minus instead of plus. So AC 1 minus Ka m of t cosine 2 pi fct. So we get the double sideband suppressed carrier wave S of t by subtracting S2 from S1, as here shown in this diagram. So S2 of t is subtracted from S1 of t, and the result will be S of t. So S of t is the subtractions of the S1 of t from and S2 of t, which is AC 1 minus Ka m of t cosine 2 pi fct. So if we simplify this expression and manipulate this expression, we will have AC cosine 2 pi fct multiplied by 1 plus AC multiplied by this expression Ka m of t cosine 2 pi fct minus AC cosine 2 pi fct into 1. It will become minus AC cosine 2 pi fct. So then we will have here actually also plus. We have here plus. I will amend these typos, inshallah, after the video, and I will send you this as soon as possible. So we have here plus, and we have here minus. Then we will find that AC cosine 2 pi fct and minus AC cosine 2 pi fct will be cancelled together, and we will be left with the AC Ka m of t cosine 2 pi fct plus, this is a plus, AC K sub A m of t cosine 2 pi fct. So we will have twice K sub A AC m of t cosine 2 pi fct. So if you compare this with the standard that we have shown earlier for the double sideband modulated signal, we will find that it is the same. That's how we generate the this one of the method that can generate the double sideband suppressed carrier signal. Just only we have a factor of our scaling factor, which is 2K sub A. Now for the process of extracting, now we talk about the demodulators, that's the modulation process. Now we talk about the demodulator. Now the process of extracting or retrieving an original message signal from DSP-SC, from the modulated wave, is known as detection or demodulation, as we have seen also in the standard amplitude modulation detection or demodulation. So demodulation is the inverse of the modulation process. So the process of extracting an original message signal from the double sideband suppressed carrier wave is known as detection or demodulations of the double sideband suppressed carrier. And we have also types of demodulators or detectors used for demodulating the double sideband suppressed carrier wave. We have coherent detector and we have Costas loop. And also in this session video, we will study only the coherent detection. So coherent detection, here is the diagram for coherent detector. Here the same carrier signal, so here we have, as in this block diagram, we have the carrier wave transmitted from the transmitter and propagated through the channel and received by the and delivered to the receiver. So S of t, this is our double sideband suppressed carrier wave. Okay, and we have our product modulators, we have a local oscillators, and we have a low pass filter. So with the help of this component, we can recover our message from the modulated wave S of t. So our message signal, B out of t, will be extracted or retrieved from the modulated signal. So the same carrier which is used for generating the S of t, the same carrier is generating the modulated signal we will use it in the receiver side as well, the same carrier. Hence the process of detection is called coherent detection or synchronous demodulation. So what I mean, the carrier signal the receiver should be in synchronous with the carrier signal at the transmitter. So the transmitter, the carrier signal at the transmitter and the carrier signal at the receiver should be in synchronous. They should be synchronized, or they should be coherent in phase and frequency. This is very important. That's why the name, hence the name, come from coherent detector. So coherent means synchronous. So the carrier signal at the transmitter should be in synchronous with the carrier signal at the receiver. So as shown here in this block diagram, then the modulated wave, or the DSPSC, will be multiplied by the locally generated carrier signal C of t, which is equal to AC cosine 2 pi FCT plus phi. So S of t will be multiplied by C of t, and the output of the product modulator is denoted by D of t, which then will be passed to the low pass filter, and then the output of the low pass filter should be the demodulated output, which is the message signal actually. Let us see mathematically how this can happen. So multiplying the signal, as we said, S of t by the local carrier wave. So this is the S of t multiplied by the carrier signal or the carrier wave. Let us see what we will have. By a local carrier wave, then D of t here, D of t, this is the output of the output of the combined S of t and C of t signals. So V of t is equal to S of t multiplied by the local carrier wave, AC cosine 2 pi FCT, where here we assume that phi is equal to 0. There is no phase shift. Having said that, then S of t is equal, V of t is equal to S of t AC cosine 2 pi FCT, and V of t, if we replace S of t, and we know that S of t is equal to M of t cosine 2 pi FCT. This is the S of t. This expression would represent S of t, as we know. This is the modulated signal, multiplied by the local carrier wave, which is AC cosine 2 pi FCT, after we assume that phi is equal to 0, or there is no phase shift, or the phase shift phi is equal to 0. So multiplied by AC cosine 2 pi fct. So we have cosine, then the v of t is equal to AC m of t cosine 2 pi fct, and cosine 2 pi fct will give us cosine square 2 pi fct. So if we use the trigonometric identity for cosine square, then we will have v of t is equal to AC, and this will be 1/2 into brackets 1 plus cosine twice the angle. So twice the angle we have 2 pi fct. So we will have twice that, it will be 4 pi fct. And we have half outside, and here we have 1. And if we multiply m of t inside after we manipulate this identity, then we will have v of t is equal to AC over 2 m of t plus m of t cosine 4 pi fct. So taking the Fourier transform, as we said, it is very easy to analyze the signal in frequency domain rather than in the time domain. So if we take the Fourier transform of this v of t, then we will have v of f is equal to, so if we multiply this will be AC over 2 m of t. So the Fourier transform for m of t is equal to capital M of f multiplied by a constant AC over 2 plus also AC multiplied here, and we will take this also we have seen earlier in the earlier slides. M of t, this is multiplications of two signals in time domain will be a convolution, and we know that the Fourier transform of cosine. Now we master what is the cosine Fourier transform for the cosine. So it is deltas, and when we multiply by m of f, is this convolution in the frequency domain, and we know that cosine 4 pi fct, now we have double 4 pi, so it will have 1/2 delta of f minus 2 fc plus 1/2 delta of f plus 2 fc, 2 because we have 4 pi. So this is will become, as we have seen, b of f AC m AC over 2 capital M of f plus AC over 4 capital M of f minus 2 fc plus AC over 4 capital M of f plus 2 fc. Now then after v of t will be delivered to the low pass filter, and the low pass filter will remove any high frequencies, right? So then as we know this 2fc, we know that fc is a very high frequency, so twice that will become much higher. So it is very easy to eliminate or to filter out these components by using a low pass filter. Then we will be left only with the low frequency component, which is capital M of f with a factor actually. So passing through a low pass filter, then V out of t, this is our output voltage here, the demodulated output signal, which is should be the message signal. So definitely V out of f is equal to AC over 2 capital M of f. So now we can transform back from frequency domain to time domain, taking the inverse Fourier transform. The output signal V out of t is equal to AC over 2 M of t. So hence we managed to retrieve or extract our message signal from the modulated DSP-SC signal. Also, we can visualize the frequency spectrum by plotting this signal as shown here. So we have these signals, and then we can use the low pass filter. We managed to block or filter out the high frequency, which are centered at 2fc, as we have seen here. 2fc for the positive and for the negative values, f plus 2fc. So f plus 2fc equal to 0, then this is for the negative part, and this is f minus 2fc is equal to 0. You set it to 0, then f is equal to 2fc. This will be for the negative part. So as we said, this component will be removed or filtered out using the low pass filter. Therefore, here we have the low pass filter, which can just only extract a very low frequency component and will reject any high frequency component like FC or twice FC. So this will be blocked, it will not pass through. We will let only the low frequency signal to pass through, which it is our message signal after using the low pass filter. So this is a low pass filter here. So coherent detection or detector is used to demodulate the double sideband suppress carrier. And as we have mentioned earlier or previously in previous slides, that we assume that the local oscillator that is responsible for generating the modulated signal for double sideband suppress carrier, so the carrier at the transmitter should be in synchronism with the carrier at the receiver. We assume that, and that's the ideal case, that they are synchronized in phase and frequency perfectly. But here in this example, we assume that there is a phase difference phi, and we would like to see the effect of this phase on the demodulation process. So it is assumed that the local oscillator signal is exactly coherent or synchronized in both frequency and phase with the carrier wave C of t used in the product modulator to generate S of t. And as we said, this is the method of demodulation is known as coherent detections or synchronous demodulation. So let us see the effect of phi. So for a more general demodulation process, we assume phi is an arbitrary phase difference. So phi is now, we assume now phi not equal to 0. Let us see what is the effect of phi now on the demodulation signal. So V of t, now it will be equal to S of t cosine 2 pi fct plus phi. Before we assume that phi is equal to 0. Now here we have an arbitrary phase difference which is denoted by phi. So let us just go through the same, and I will go in these equations very quickly, a little bit quickly, but it is the same steps. So V of t, which is the V of t here, which is the output of the modulated signal S of t and the carrier locally, or the local carrier signal at the receiver. So multiply together with the product modulators, then we will have AC M of t cosine 2 pi fct multiplied by cosine 2 pi fct plus phi. Now also, now we have cosine cosine, so it will have AC M of t over 2 cosine phi plus cosine 4 pi fct plus phi. Now we have phi. Let's do the same multiplications. Cosine cosine. Okay, so the second equation or the second term in the equation is removed by low pass filter. This also will be removed because still we are using a low pass filter here. So we remove this term because this term is centered at twice FC. Okay, so we will be left with AC M of t over 2. Now we have cosine multiplied by cosine. So therefore, V out of t now is equal to AC M of t over 2 cosine phi. Before, the ideal case, when phi is equal to 0, we don't have this factor, cosine phi. Now we have cosine phi. Now let us see what is the effect of cosine phi on the V out of t. So also this is again the frequency spectrum of the signal. So V out of t is proportional to M of t when the phase error phi is constant. So if phi is constant, this will V out will be proportional to M of t. So it will be attenuated by a factor equal to cosine phi when it is constant. So V out of t will equal to AC M of t over 2 when phi is equal to 0. This is as we have seen in the previous explanation. Because cosine 0 is equal to 0. Here we have here cosine, if phi is equal to 0, then cosine 0 is equal to 0, cosine 0 is equal to 1, and 1 multiplied by this, it will give us the same value. So it will be, this is when V out will be maximum. So if now phi is equal to plus or minus 90 degrees or pi by 2, then we know that cosine pi by 2 is equal to 0. So this V out minimum will be 0. And this effect, we call it the quadrature null effect. So when the phase error is constant, the detector provides an undistorted version of the original baseband signal M of t. So if phi is or cosine phi or the error phi is constant, because phi is the phase difference between the local carrier at the receiver and the frequency or the signal at the transmitters, which is represented in the modulated signal S of t. So this is the effect that cosine phi will occur. So the practice, in practice, we usually find that the phase error varies randomly with time due to random variations in the communication channel because of fading and noises, etc. So the result is that the detector output, the multiplying factor cosine phi, also varies randomly with time because the channel is randomly changing, which is obviously undesired. If phi, cosine phi, this factor, because phi will change with the variations of the channel, then will have an undesired effect. So therefore, provision must be made in the system to maintain the local oscillator in the receiver in perfect synchronism in both frequency and phase with the carrier wave used to generate the double sideband suppressed carrier modulated signal in the transmitter. So in simple words, the transmitter and the receiver, the carrier signal should be synchronized in terms of phase and frequency. They have to be perfectly in synchronism. Otherwise, we will have undesired effect. The resulting system, hence, complexity is the price that must be paid for the suppressing the carrier wave to save the transmitter power. As we said, the double sideband suppressed carrier solve one of the problems that the AM standard modulation technique, which suffers from waste of bandwidth and waste of transmitted power. And double sideband suppressed carrier solve the problem of the transmitted power. The DSPSC save the transmitted power actually by suppressing the carrier. But the price that we pay is what? Is the complexity of the design of the receiver. Because the transmitter and the receiver should be in synchronism. So now let us take a special case for double sideband suppressed carrier when the message signal M of t is a tone modulation, which means that tone modulation, that means it has a single frequency. So now we will consider now the modulated signal now instead of general M of t, then M of t is equal to a sinusoidal signal. which is equal to AM cosine 2 pi FMT. And the carrier signal, C of t, is equal to AC cosine 2 pi FCT. So mathematically, we can represent the equations of double sideband suppressed carrier wave as the product of the modulating and the carrier signals. So we will go through the same steps, but now instead we use a sinusoidal signal, which it has only one frequency FM, and which is called tone modulation or single tone modulation. So S of t is equal to the product of the message signal and the carrier signal, and we know that it will give us AMAC cosine 2 pi FMT multiplied by cosine 2 pi FCT. For bandwidth, we know that the formula is F maximum minus F minimum, that definitely, right? And we get also here the bandwidth is equal to 1. Consider the equations of double sideband now. S of t is equal to AM cosine 2 pi FMT into cosine 2 pi FCT. So we have cosine for two angles, cosine A, cosine B. We use the trigonometric identity. Then S of t is equal to AM AC over 2 cosine 2 pi FC plus FMT. The summation of the two angles, cosine, the summation, plus cosine the difference between the two angles. So AMAC over 2 cosine 2 pi FC minus FM. So from here we find it's very clear that we have the maximum frequency FC plus FM and the minimum frequency FC minus FM. So from the formula for the bandwidth that we can use to calculate the bandwidth is F max minus F minimum, and we know that F max is equal to FC plus FM, and F minimum is equal to FC minus FM. So if we subtract F max, F minimum minus F max, then we will get the bandwidth is equal to twice the message signal frequency FM, where FM is the highest frequency component in the message signal. And in the case of the sinusoidal wave, we have only one frequency component, which is FM. Thus, the bandwidth of the double sideband suppressed carrier wave is the same as that of AM wave, and it is equal to twice the frequency of the modulating signal. So this is still a waste of what? A waste of channel bandwidth. So double sideband suppressed carrier solve the problem of the transmitted power by suppressing the carrier, because the carrier has no information. But still, the double sideband suppressed carrier TSPSC modulation suffers also from the waste of channel bandwidth. Now let's see the power calculations. Also, S of t is equal to AMAC over 2 cosine 2 pi FC plus FMT, and this is the same equation, AMAC over 2 cosine 2 pi FC minus FMT. So we know that now we don't have, as we have seen here, in the AM signal, we have a third component, which is the pure carrier component. But now we don't have pure carrier component. We have only just double sideband, the upper sideband and the lower sideband. So then the total power here is equal to the upper sideband plus the lower sideband. And we know how to calculate the upper sideband and the lower sideband. So upper sideband is equal to AM squared, AC squared over 8, and lower sideband is equal to AM. It is the same as the upper sideband. So then the total power is equal to twice this value. So it will be AC squared, AM squared over 4. So the total power is equal to over 4. Now I would like to ask you to think about what is the power efficiency of the double sideband suppressed carrier. We have seen that in the AM modulation, that the efficiency is approximately equal to one third, or approximately equal to 33%, or one third, and two thirds of the power is wasted in the carrier. Here we don't have carrier signal. We have only just upper sideband and lower sideband. Now I'm asking you guys to think about what is the power efficiency of the double sideband. This is left for you as an exercise. So here we have a homework for you to solve. In the figure below, if the modulating signal m of t is equal to 4 cosine 1000 pi t, and the carrier frequency is 1 megahertz, fc is equal to 1 megahertz, we would like to find s out of t. So we have the modulated signal, dsbsc, s of t signal, which is equal to m of t cosine omega ct, and this is the local carrier at the receiver, and here we have a low pass filter represented by these characteristics, and here we have s out of t. We need to find s out of t, which is one of these answers. Also, this is homework. So this is maybe the same as the previous exercise of homework. Here we consider now our modulation, tone modulation. Now we consider only the message signal is sinusoidal wave, which is equal to cosine 2 pi fmt. And here we have the carrier. This is how we generate the double sideband suppressed carrier signal, but using the tone modulation signal. So will be cosine 2 pi fct multiplied by the product multiplier. So cosine 2 pi fmt multiplied by cosine 2 pi fct will become cosine 2 pi fm into cosine 2 pi fct. So using this trigonometric identity, we can use to manipulate or express this in this form, straightforward. So cosine 2 pi fm, we know that using the Euler identity, again, that's very helpful to analyze the signal, as we said, in the frequency domain rather than in time domain. So we will use this Euler identity to express the cosine 2 pi fm in the complex exponential components, e raised to j2 pi fmt plus e raised to minus j2 pi fmt. So if we find the Fourier transform for this, it is first part is equal to half delta of f minus fm plus delta of f plus fm. And if you plot this and to see the spectrum of the this signal, then we will have this is as a pulse located at f minus fm equal to 0, then f is equal to fm. So this is centered in the fm. So this is a pulse and represented by this arrow, and it has a magnitude of 1/2. And this is for the negative f plus fm equal to 0. So f is equal to minus fm. So this is for the negative or image of this pulse. Also it is delta, so it is pulse here, and it has a magnitude of 1/2 as well. So if the amplitude here is AC, for example, then it will be half AC. So we have two frequencies located at FM and minus FM. So this is for the cosine. Now, so this is again here. Now for the product of the two cosine 2 pi FM into cosine 2 pi FCT. It will be using the trigonometric identity as well. We will express it as shown here in this equation. So try to find now the Fourier transform of this cosine and this cosine as well, and then plot it to see and to visualize the spectrum of this signal. So for this, it will have half delta of f minus fc plus fm plus delta of f plus fc plus fm. So this is for this cosine. And for this, we have half delta of f minus fc minus fm plus delta of f bracket fc minus fm. So if you plot this, you will find this component have centered at fc plus fm. We have a pulse here with a magnitude of half, and minus fc plus fm, which is this part, this pulse. So this represents this one, this component, and this component. This is the Fourier transform. And for the second one, this will be represented by fc minus fm, this component, and this component is fc minus fc plus fm, this component. So this component here, and this one is fc minus fm here. So it is very important to know that this will help you to solve this this exercise. So it is recommended to solve this exercise by understanding this very carefully. Okay. So thank you very much, and I hope this is have been informative to you, and I would like to thank you for viewing, and see you inshallah in the upcoming videos. Stay tuned and see you soon. Assalamu alaikum wa rahmatullahi wa barakatuh.